In this slidecast, we'll talk about implementing the hash table. Here is the hash map abstract data type that our author implements, in his own namespace in our textbook. It has begin and end, which return iterators. We have an empty function, Boolean. We can get the size, which returns the number of entries in the map. Here's insert, where we can insert an entry into the map. We can remove an item from the map. We can find an item. It'll return an iterator referencing that item. And here's our overloaded subscripting operator, so we can return a reference to the value associated with the key. Now, if the key is not associated with the value, it inserts a default value into the map and returns a reference to the inserted object. So entry type is defined as follows. So entry type def in C++, we can have this pair type from the standard library. Remember, a pair consists of a key and a value. And this is a template for, we can have key types and value types. So this type definition is associated with this, we can have a single word entry type to refer to this pair type. Now, the data fields class hash map is as implemented by the hash table open.h is as follows. We have the function object that will compute the hash function for the key type. We get the number of the keys in the table. Here's the hash table, which is a vector of pointers to entry types. So our vectors contains pointers, and remember the entry types are these key value pairs. The table has an initial capacity. We have a load threshold, which is the maximum load. We track the number of deleted keys. We have a dummy entry that represents the deleted keys, and here's a pointer to the dummy entry. And we're going to use this to implement our open addressing. So here's our class hash map. Here's our entry type. Here's a constructor to construct an empty hash map with no keys. It has an initial capacity. The threshold is 0.75. Here's some private fields. We have our hash function that we can use to generate the hash code for a given key. Here's some other parameters. We've got our table, the definition we saw earlier, and the initial size is going to be 100. We've got our load threshold, the number of deletes. And here at the end of our hash map class definition, here we've got two declarations. The first one here is declaring our dummy entry, and here is the reference to our, where deleted is a reference to a dummy entry. Now the locate function returns the index of the specified key if it's present. Otherwise it returns the index of the first available slot. And then rehash doubles the capacity of the table and permanently removes the deleted items. We'll call rehash when we reach our threshold, when our map fills up enough that it reaches 0.75. So here's the algorithm for the locate function. We set the index to by taking the mod of the hash code, and we mod by the table size. And then while we don't find that index, it's not empty and the key is not at that table, we'll increment the index, mod the table size. And finally we'll return the index, which will point to the entry where we find the key or the next available entry. So here's our locate function that takes a reference to a key. We'll first generate the index, and then while that index entry is not full, and while that entry is not equal to null and it's equal to deleted, or the entry that's stored there is not equal to the key, we'll continue to index the key and wrapping around when we reach the end. And then finally we'll return that index as the result. So insert, we first check for the need to rehash, then we find the first table element that's empty or that contains the key, and if it's an empty element, then we insert the new key, we increment num keys, and we return the pair, which is an iterator to the inserted item in true. And if the key was found, then we make a pair of the iterator and return the value false. Remember, we say false, meaning the insert failed because the key was already there. So here is our insert function that supports that algorithm. You could pause here and read through the code and make sure you understand each step. I'll let you do that on your own. Now the subscript operator, we call insert to insert a new entry consisting of the key and a default value type object. And we use the iterator returned from the call to insert to return a reference to the value that corresponds to the key. And here's our overloaded insert operator. And at first we generate an entry type for that key and the default value, and we try to insert it. And if that key already exists, then the iterator is going to point to the pre-existing key value pair. And if it doesn't, it'll refer to the default value, and then we'll return a reference to that value. And remember, the value is the second item in the pair. The algorithm for erase is to find the first table element that's empty or the table element that contains the key. And if the key is found, then we'll remove this table element by setting it to point to deleted, and we increment the num deletes and decrement num keys. Now we'll call rehash to allocate a new hash table that's double the size. We'll reset the number of keys and the number of deletions to 0, and then we'll reinsert each table entry that has not been deleted into the new hash table. And here's the code for doing rehash. We'll first create other table, which will be 2 times the current table size. We'll swap this table with the current table, and then we set the number of deletes to 0, and we'll reinsert all the items from the old table into the new one. You could pause and spend time to understand every line of this code. Now, because the vector table contains pointers to dynamically allocated entry types, we have to implement copy constructor and the assignment operator so that they can make copies of the objects pointed to when the hash map is copied. Okay, so we do that, remember, to do deep copies. Remember the rule of 3 that we talked about earlier in the book. And we also need to delete these dynamically allocated objects when a hash map is destroyed. Now, class hashMap is implemented by this hashTableChain.h. This is where we'll have do chaining. We'll have a hash function object, the number of keys, a vector of lists containing the items. We'll have the initial size of the vector and a threshold. And here's the definition of the hashMap class. It's similar to the unordered map. Here we have a hash map. We have entry types. Here's how we construct an empty hash map. We have our hash function object. Here's a vector of lists containing the buckets. So the buckets is a vector, and that vector is a vector of lists of entry types. Now to insert, first we check for the need to rehash. Then we set index to be the hash code mod, the size of our vector. And then we search the list at the buckets to find the key. If it's not found, then we can append a new entry to the end of the list. And then we call makePair to return an iterator to that inserted item. Or else we indicate that it's not found. And here is the insert function. It returns a pair. Remember, that's an iterator, and then the Boolean value to indicate whether the insert succeeded or not. It takes a reference to an entry as input. We check for rehashing. We generate the index for that position, and then we search for the key using an iterator over the list. And if it's not in the table, then we'll push that entry to the back of the list and return an iterator and a true indicator that indicates that we inserted a new key into the table. Otherwise, the key already exists, and we'll return a pointer to that and the indicator false that'll tell us that that key already existed in our table. Now the erase function, we generate our hash code and we search the list to find the key, and if the search was successful, then we erase that entry and we decrement the num keys. Now because hash table chain uses this vector of a list of entry types to hold the hash table, then the default copy constructor and assignment operator need to make a deep copy of the hash map, and the default destructor will delete any dynamically allocated objects. So again, we apply the rule of 3 to our hash table because we want a deep copy. Now to test our hash table implementation, we need to write a method to create a file of key pair values. We can read those key pairs from the file and insert them into the hash table and observe how the hash table is filled. We can write a toString method to capture the index of each non-null table element and the contents of the table element. And for open addressing, the contents consists of the string representation of the key value pair. And for chaining, an iterator could traverse the lists and append each key value pair to the result of the string. And the cases we might want to examine to test our implementation, we want to know, does the array index wrap around as it should? Are collisions resolved correctly? Duplicate keys handled correctly? Are deleted keys retained in the table but no longer accessible? Does rehashing occur appropriately? We could step through the insert method and observe how the table is probed and examine the search chain followed to access or retrieve a key. Now, alternatively, we could insert randomly generated integers into the hash table to create a large table with little effort. And here's how we can do that, using the random function. And then insertion of randomly generated integers into a table allows testing of tables of very large sizes. It's less helpful for testing for collisions. And after the table is complete, we can interactively enter items to retrieve, delete, and insert and verify that they're handled properly. Now, if you're using open addressing, you can add statements to count the number of items probed each time an insertion is made. And you can total and divide them by the number of assertions to determine the average search chain length. And if you're using chaining, you can also count the number of probes made and display that average. And then after all items are inserted, you can calculate the average length of each linked list and compare that with the number predicted by the formula discussed in section 9.3. And that brings us to the end of this slidecast.